a functional equations question, an Olympiad functional equations question. As you can see on the screen, it states that find all functions f from the positive reals to the positive reals such that f of x plus f of x plus f of y is equal to 2f of x plus y. So before we actually go into this, we need to see what type of information we're working with. So we can't actually test for, cannot test for x, y being equal to 0 because 0 is a non-positive and non-negative number, so we can't use that. So what is like the next natural progression? We can't say useful tests we can't really think of right now. So let's maybe try find something about the function. Namely, let's try to test if it's injective. And the reason I say that is because I can see that a variable is inside and outside of a function. And what I mean by that is this here is inside and this is outside. So my natural instinct is going to be trying to test for injectivity. So number one, test for injectivity. We're going to let f of a equals f of b. And if we use the equations and find out that a equals b, we've proven that this is actually injective. So let's sub in a to be equal to y. So I have that f of x plus f of x plus f of a. And that's going to be equal to 2 times of f of x plus a by the equation above. And then also I'll do the same thing for b. So f of x plus f of x plus f of b is equal to 2f of x plus b. Now notice that these two are equal because f of a is equal to f of b. Now, because those two are equal, we can equate the right-hand sides. So 2f of x plus a equals 2f of x plus b. Cancelling out the 2f of x, we get that a equals b. So this is injective. We've proven that. Nice. So we found out the uniqueness of one input gives a unique output. So what we can do after that is we can try maybe find out some sort of key identity, or we can try to prove something else about the function. The next thing I will do is this function is, we'll try to prove for surjectivity next. So prove for surjectivity. Now, let's look back at the original equation and so f of x plus f of x plus f of y is equal to 2f of x plus y. And then I'm going to sub in some sort of, for a greater than 0, I'm going to sub that in for x. So f of a plus f of a plus f of y is going to be equal to 2 times f of a plus y. So as y ranges over any values over some positive real values, any number is going to be greater than 2f of a. So this function here will range over all values greater than 2f of a. So how should I say this? It's like for every single number that you have, for every single input, let's say suppose capital T is going to be greater than 2f of a. Or in other words, that means that there exists some u such that f of u is equal to capital T, which is greater than 2f of a. Nice. So we've proven that it's surjective after a point. After 2f of a, it's going to be always surjective, or after 2f of x, it's going to be always surjective. So now let's try to derive a key identity. So number 3, key identity. Now let's go back to our original equation, f of x plus f of x plus f of y is equal to 2f of x plus y. And then I'm going to call this inside input here capital A. Now, by calling this capital A, I'm going to use that input. I'm going to rewrite the equation. So I'm going to use it back into the equation. So f of A plus f of A plus, Now, I'm not going to use y again because y is within a. So I'm going to say, let's say some f of z is equal to 2f of a plus z. Now, we need to expand this. So we have f of x plus f of x plus f of y plus f of x plus f of x plus f of y plus f of z is equal to 2 times of f of x plus f of x plus f of y plus z. Now that's has a very long equation, but it actually works out quite nicely because it's referring to itself twice, and we can simplify this down quite nicely as well. So we get that f of x plus f of x plus f of y is equal to, sorry, not equal, plus 2f of x plus y plus f of z is equal to 2 times of 2f of x plus y plus z. Now we just collect terms, so we get f of x plus 3f of x plus y plus f of y plus f of z is equal to 4 times f of x plus 2y plus z. Now that we have this equation, we need to make some sort of like a smart substitution. So let's consider 2f of x plus 2y plus z. Now let's try to use this as a substitution for y in the very first given equation. So f of x plus f of x plus f of 2f of x plus 2y plus z is equal to 2f of x plus 2f of x plus 2y plus z, which is equal to 4f of x plus 2y plus z. Now that we have this, this is the exact same as this, and thus we have made a very smart consideration, and we can thus equate, since these two are equal, this and this must be equal. Now we can equate these to then obtain that f of x plus 3f of x plus y plus f of y plus f of z, and then we can equate that, make that equal to f of x plus f of x plus f of 2f of f of 2 f of x plus 2y plus z. Now this doesn't look as much simpler, but we do get a quite nice, like, we can actually derive something very nicely from this, and it's that since we know that f is injective, these two inputs must be the same. So x plus 3f of x plus y plus f of y plus f of z must be equal to x plus f of x plus f of 2f of x plus 2y plus z. We can cancel an x out, we can cancel an f of x out to get that 2f of x plus y plus f of y plus f of z is equal to f of 2f of x plus 2y plus z. I have this like very large equation. I'm going to subtract the input from both sides, and so give me something very interesting. F of 2f or f of x plus 2y plus z minus 2f of x minus 2y minus z is going to be equal to f of y minus y plus f of z minus z. Now our right hand side is actually very interesting. And the reason it's very interesting is because we can now introduce a new idea, which is the fixed point idea, which says, so fixed point we want to introduce some sort of f of p minus p being equal to f of q minus q for some sort of arbitrary p and q. So what we're going to do that is we're going to use the fact that f is surjective after 2f of a, and we're going to choose a large number s such that s is greater than 2f of a, and s minus p is greater than 2f of a, and s minus q is also greater than 2f of q. Sorry, 2f of a. S minus q is going to be greater than 2f of a. And then using the surjectivity argument from before, there exists some sort of x1 such that f of x1 is equal to s minus p, and then f of x2 is going to be equal to s minus q. So f of x1 plus p is equal to s, and then f of x2 plus q is equal to s. Now, once we have these two, we can try to use the original equation that we had before and try to find some sort of simplification. And by doing this, we can actually find some very nice substitutions. So let's try that x equals x1 and then that y is equal to p. And then what we can do from there is, let me just zoom out so I can refer back to my own equation. F of 2 times of f of x1 plus 2p plus z minus 2f of x1 minus 2p, plus 2p plus z is equal to f of p minus p plus f of z minus z, right? And then notice how this and this is just equal to 2s, so f of 2s plus z minus 2s minus plus z is equal to f of p minus p plus f of z minus z. Now I'm going to do the exact same thing with q. So let's test x equals x2 and y to be equal to q. And then I get that f of 2, f of x2 plus 2q plus z minus 2f of x2 plus 2q plus z is equal to f of q minus q plus f of z minus z. And then I can use the same thing, which is I can recall s and get that to f of 2s plus z minus 2s plus z is equal to f of q minus q plus f of z minus z. Now this is very nice. We have two very identical equations. We can equate this and we can equate this. F of p minus p, and then I can cancel out the f of z minus z, so I get that f of p minus p is equal to f of q minus q as required. So now that we've proven that result, we have shown that if since p and q are arbitrary, that there is a constant c such that f of t is equal to t plus c. We've shown that this equation is now linear. So now we just need to somehow find what this constant is. So we're going to sub this back into the original equation. Remember that we had f of x plus f of x plus f of y. This is going to be equal to, let's look at the inside first, f of x plus c plus y plus c. And then this, we're just going to add c to all of this, so it's going to be 2x plus y plus 3c, because we need another c, and that's going to be equal to 2 times of f of x plus y. 2x plus y plus 3c is equal to 2 times of x plus c plus y. 2x plus y plus 3c is equal to 2x plus 2c plus y. Y is cancelled, 2x is cancelled, 3c is equal to 2c, which can only mean that c is equal to 0. Thus, f of t equals t, and we have our solution, which is f of x equals to x. And that is our only solution for this problem. This is a very difficult problem, a really difficult problem, and it has quite a lot of steps, but I think And also my handwriting got a lot bigger as we went down. That's, I mean, that's a new size thing, but